Mình đã qua màn hình chưa? Mình đi hả? Oh, được rồi. Hello, teacher and classmates. We are Team 3, and today we are going to talk about assembly language. Our team members are me, Vũ Thị Thanh, Nguyễn Thị Huyền Trang, Nguyễn Thị Trung Vui, and Nguyễn Minh Huy. In this presentation, we will explore what assembly language is, how it works, and why it's still important in computer system today. Although assembly may seem complicated, it helps us understand how computers actually operate at the hardware level, much closer to the CPU compared to high-level language. Now let's move to the next slide to see what we are going to cover today. Here is the outline of our presentation. First, we will start with an overview of assembly language. Second, we will talk about differences between assembly and high-level programming language, such as Python or Java. Third, we will discuss the main components of assembly and its basic syntax, including labels, instructions, and operands. Next, we will explain register and the 86 and x64 architecture, which are essential for how the CPU handles data. After that, we will show some basic assembly instructions to demonstrate simple operation. Then we will go through to the advantages and disadvantages of using assembly language. And finally, we will end with an assembly program example, a division operation. So now let's start with the first part, the overview of assembly language. Assembly language is a low-level programming language designed to communicate directly with computer hardware. Assembly acts as a bridge between machine language and high-level programming language such as C++, Java, Python. Each instruction in assembly typically corresponds one-to-one with a specific machine instruction. Instead of being written as a hard-to-read sequence of zeros and ones, programmers use mnemonics, for example, MOV, ADD, SUB, JMP to represent these instructions. It makes assembly code easier to understand than poor machine code, while still allowing very detailed control over the hardware. Assembly enables programmers to interact closely with the CPU and memory. Program written in assembly do not require interpretation by a high-level runtime environment. Instead, assembly code is translated directly into executable machine code by an assembler for the CPU. By eliminating many layers of abstraction, program written in assembly can achieve very high performance and utilize the hardware capability for the maximum extent. However, due to the lack of abstraction and the need for the manual management of many details, assembly requires programmers to have a deep understanding of computer architecture and take more time and effort to develop compared to high-level language. Now let's move to the next slide about the differences between assembly and high-level programming language. In terms of abstraction level and operation, assembly differs significantly from high-level programming language. Assembly is closer to the hardware. Assembly instruction correspond directly to the CPU's machine instruction, whereas high-level language are more abstract, allowing programming without concern for hardware details. For example, for instance, in C++ or Python, a single simple statement might compile into multiple complex machine instructions, while in assembly, the programmers must write out each specific instruction to control the CPU. Regarding memory management, high-level language often feature automatic mechanism that free programmer from detailed management of memory allocation or delocation. Conversely, assembly program forces the developer to manage memory manually, taking responsibility for allocation and delocation, and optimizing every every byte of memory if needed. This increase the risk of error, such as memory leaks, if the programmer is not careful. A major difference of is the portability of the program. Code written in a high-level language can run in many different types of machines and operating system with a little or no modification, provided a suitable compiler or virtual machine is available. In contrast, assembly code is inherently tied to a specific CPU architecture, typically running on a running only on a certain type of processor. If migrating it to different architectures, for example, from x86 to ARM, the assembly program must be almost completely rewritten. In other words, high-level language have high cross-platform capability, while assembly is less flexible but allowed to for specific optimization for a particular machine architecture. Xong rồi á.
Next, I will talk about the next two parts. First, we will look at main components of assembly and basic syntax. Assembly source code consists of the following basic components: label, opcode, instruction, operand, and comment. A typical line of assembly code follows this format. Label, an identifier attached to a location in the program, usually at the beginning of a line. Labels are used as reference point for jump or call instructions. Example, start could be a label marking the beginning of a code segment of code instruction. The command the CPU will execute each instruction performs a specific operation. Example, data transfer calculation or program flow controls. Instructions are represented by mnemonics such as MOV and at operand. The object that the, in, the instruction operates upon. Operands can be register, immediate values, construct, or memory address. For example, the instruction at EAX file has the register EAX and the constant file as operands. Comment start with a semicolon. This part is neither translated nor executed. It's solely for the reader to better understand the instruction functions. Next, we will talk about register and x86 or x64 architectures. Register are small, very fast storage locations inside the CPU used to temporarily hold data and addresses during processing. Each CPU architecture has its own set of registers, which are central to assembly programming. For example, on the x86 22-bit architectures, Common resistor include AX, BX, CX, DX general purpose resistor, SI, DI, index resistor used for array or string operations, BP, SP, stack related resistor, base pointer and stack pointers, and IP instruction pointers resistor, holding the arrest of the next instruction on modern x86 system. These resistors are often extended to 22 bits and prefixed with E extended. Example EAX, EBX, ECX, EDX corresponding to the 22-bit extension of AX, BX, CX, and DX. The x86-64 x64 architectures, the 64-bit extension of x86 further increased the size of these resistors to 64 bits, changing the prefix to R like RAX, RBX instead of EAX, ABX, while also expanding the number of general purpose resistors from 8 to 16 resistors. As a result, x64 CPU can process large 64-bit data directly and access very large memory regions, many terabytes that 22-bit CPU cannot manage. The x86-64 architectures also introduce additional extended resistor R8, R15, and other enhancements, boosting processing performance. It's important to note that assembly code written for a 64-bit environment differ from 22-bit due to the use of different instruction sets and resistors. However, most x86-64 microprocessors still have a compatibility mode to run 22-bit and even 16-bit code to ensure backward compatibility with older programs.
And I will introduce about basic assembly instructions. Assembly provides many instructions to manipulate data and control program flow. Here are some common assembly instructions and their functions. The first one is data movement instruction. MOV copies data from a source to a destination. There are also push and pop to place data onto or pop data off the stack. An automatic instruction add two operands, subtract one operand from another. Mode multiplication, and diff division. These instructions typically operate on register or between a register and a constant. The result of the calculation may be stored in a register. And logical instructions and or XOR perform bitwise logical operations on operands, not inverse. The bits O become 1, but 1 become O. These instructions are useful for bit manipulation and creating bit math. And another is control flow instruction. JMP unconditional term to a label. And there are also conditional term instruction like GE term if equal, JNE term if not equal, JG term if greater, JL term if less. These instructions are often used immediately after a comparison to decide the program path. The last is call and return instruction. Call involves the execution of the procedure or function. Read ends the function and return to the instruction location immediately following the previous code instruction. These commands allow the program to be organized into subroutine or functions similar to high-level languages. And about symbol illustration set example. The assembly code segment below illustrate how to add the two number 5 and 7 in the x86 architecture. Look at the picture. I will explain to you. First is AX loaded with the value 5 and EBX with 7. The instruction at EAX and EBX causes the CPU to take the content of the two registers EAX5 and EBX7 and add them together. After execution, the EAX register would contain the result 12, while EBX remains 7. Thus, we have performed the addition 5 plus 7 by directly manipulating the CPU register using the appropriate assembly instruction. Instead of writing C equal A plus B as in C, for example, we must use corresponding move and add instruction. And I will introduce about advantages and disadvantages of assembly. About advantages, we have high performance. Well-written assembly code can be optimized to the maximum extent for specific hardware. Programmer can control every machine instruction and detailed hardware control. Assembly allow direct access to system resources such as register, memory, I/O port at the lowest level. Programmer can customize how data is stored and how the CPU is skilled. And small program size due to being written at the very low level. Assembly program often have a smaller binary file size compared to program with the same function written in a high level language. And the last is system in understanding, although not a direct advantage of the language itself. Learning assembly have programmer gain a deep understanding of computer architecture, the working principle of the CPU, memory management, and program optimization. This knowledge help writer more optimized and efficient code in high-level languages. And about disadvantages, we have high complexity. Assembly is very close to machine code, so its syntax and concept are much more difficult to grasp than high-level languages. To write a programming, the programmer must have a true understanding of the CPU architecture, instruction set, register, and memory management. And we have time-consuming development. For the same function, assembly code is generally more verbose and take more time to write for. And the last we have difficult to maintain and understand. Assembly code is generally harder to read and understand because it doesn't carry as much intuitive meaning as high-level code. If an assembly programming is not carefully commented, debugging or upgrading it later become very challenging. And the last is Nguyễn Minh Hy.
Má khổ thiệt. Nói gì ta? Today I would like to explain a simple assembly program that performs a division operation using register AX, BX, and DX. This program demonstrates how to divide one number by another using div instruction in assembly language. The goal of this program is to divide the value stored in the register AX by the value stored in register BX. After division, the quotient will be stored in DX and the remainder will be stored in AX. This helps us understand how assembly handles mathematical operation directly on register. Look at the code on the screen. First, we move the number 100 into register AX and 7 into register BX. That means AX will be the divided and BX will be the divisor. Next, we clear DX to 0 using the instruction XOR DX DX. This is important because before any division, DX AX together represent the full number being divided. If we don't clear DX, we might get the wrong result. Then we use the div bx instruction to divide by bx. After this division, the quotient is automatically stored in AX and the remainder is stored in DX. However, in this program, the question asks us to store the quotient in DX and the remainder in AX. So we use the instruction XCHG AX DX to exchange their value. In summary, this program shows how the div instruction work in assembly. It teaches us how to, to, to map the equation. Processor automatically store the quotient in AX and the remainder in DX. After division, by using XCHG, we can swap them according to the requirement. This is a small but very useful example to understand how the data move between registers during the automatic operation. In the end, thank you for your listening. If you have any question, just ask us. I will answer it.